Good morning, sir.
Yeah, good morning. So, yeah, right. There are around 90 students. Yeah, I have started the recording. Okay. So, so any questions in the last lecture? Okay. Okay. So let me share the presentation. So, hello. Yeah. Yeah. Is this slide is visible? Hello.
Yes, sir, it is visible.
Yeah. Right. Okay. So, yeah, the last so far we are discussing about different aspects of the instruction set architecture. It means a varieties of instructions, the machine level instructions that are used that can be used that can be directly implemented by the hardware, and whereas the actual application programs are in high level language, and the instructions that whatever we are discussing in the last 2 3 lectures and all, so these are the actual instructions that are implemented by the hardware or the processor and all, right? So in that we just we are discussing about different aspects of, because we know the high level language program, how the programmer will write and what are the different things that were involved in that high level language program and all. So in view of that, we are discussing each of them with respect to various operators, then the loops, and then the procedure calling, so on, one after another and all. Right. So and today we'll just in today's the first lecture, we'll try to complete this part of instruction set architecture. So in that, actually, we have discussed earlier, that is in the previous lectures, about using directly the constants in the while performing some operations like either arithmetic operations or whatever. We are using a constant as part of the instruction. It means that whatever the data item that is required, that is available in the instruction itself directly. We need not fetch from the either a register or from a memory and all. So that way you can speed up the like operation. So it's not to be immediate operands or immediate format of the instructions and all. So with that immediate field, you can able to see that the constants can be represented or can be accommodated only in the 16 bits, because in the total instruction word length itself is 32 bits. Out of that, the lower side, the 16 bits are allocated for or meant for representing the constants. So most of the times the constants are for smaller size, so the 16 bits are mostly sufficient. But suppose if we want that, actually, if we want to deal with the higher constant size, higher size of constants, like which can be more than 16 bits. So in that case, the MIPS can allow up to 32-bit constant, can be allow up to 32-bit constant, but it cannot, there is no way to keep accommodate a 32-bit constant directly, because if you want to use a 32-bit constant, then the entire 32 bits of the like MIPS instruction itself will be occupied by the constant. So we can't do that because each instruction should have some opcode and some other control information is required. So we can't do that. So there, but the MIPS supports the 32-bit constants using the two instructions this way. Like it will split the 32-bit constant into two parts, like the lower 32-bit is the lower 16 and a half, upper 16-bit constants and all, and then it will merge them into the and then to be put it into the register and all. Like for example, if you look at here, suppose this is the 32-bit constant, whatever it was mentioned here, in the higher side, in the higher half or in the upper 16 bits. So the value is about 61, and in the lower one, the value is about 2304. The value is about 2304. So this is just a binary equivalent. From this binary, you can just, if you can derive the decimal number, it is like 2304 from the lower side, and the upper side, if you just convert this binary into the decimal, it is nothing but 61. So the total is a 32-bit constant, and if you want to use this 32-bit constant in the MIPS instruction, so the way you can deal with this 32-bit constant will be, first we will shift the upper 16-bit constant into some register, and then afterwards the lower 16-bit constant will be added to will be odd with the register content, so that the entire 32-bit constant can be loaded into the register directly, can be loaded into the register. So for that you can see here, so this is your 32-bit constant. First we are loading these upper 16 bits into a register, and that means using this LUI, that means load upper immediate. So this 16-bit constant corresponds to 61. So therefore the 61 will be first loaded into the register which occupies the upper 16 bits, that 16 bits towards the MSB side, most significant side. And then immediately the lower side will be filled up with zeros. Lower side will be filled up with zeros. Now S0 contains the 61 in the upper half, upper 16 bits, and then the lower side will be filled up with zeros. Then to get the remaining portion, we can do the R immediate S0 with the 230 for whatever the lower side, the lower 16-bit constant. This is equivalent to the 2304. So R immediate S0, 2304. 2304 is the 16-bit constant at a lower 16 bits, and then S0. So this is R with these two, and then this is nothing but this one R of, this is the lower 16 bits, this one, and then this is and then the together will be, you will get the desired 32-bit constant and all. Right. So this way you can able to manage the 32-bit constants in the using the MIPS instructions. So this is the same thing, whatever I just mentioned. This is the desired constant to be loaded, and we'll take the first upper 16 bits, that is nothing but 61, the value decimal 61, and afterwards we are logically or immediate with the lower 16 bits, so that you can get the desired the 32-bit constant. Yeah, the next thing what we are going to discuss here is that in case of branch addressing, how the address will be calculated. Like we have come across actually for moving the control, you have two types of branching. One is that conditional branching, and other one is the unconditional branch. Conditional branching means what we have seen: jump equal, jump on equal, jump if equal, or jump if not equal. So these are the two MIPS instructions can be used for branching with respect to the conditional operator. And the other one is that this unconditional jump. It's a simply jump instruction, J, jump, and then we have some address will be given. So for that, actually, there is no need for any condition to be evaluated. Simply the control has to be transferred to the address mentioned in the instruction itself. So in these two cases, how the address will be calculated, the final address will be calculated. We know that in case of load and store and all, the address will be calculated with respect to by using the base register. There is a base register which contains the starting address of the array or some pointer, some address location. With respect to that address location, then offset will be added. Offset will be added. So that is a way. In case of memory, you can able to get the address. You can compute the address. So with that, you can fetch the desired words, desired values and all. And here, in case of a branch address, how do you compute the address? So you know that in case of a branch, first we'll deal with the branch conditional, where the branch conditional address for the instruction format will be, it's of immediate format, right? Immediate format means the 16 bits, the last 16 bits will be meant for the address or the value in case of immediate one, and the remaining 16 bits contains the opcode followed by the two register operands used to be there. In case of branch conditional, so the operands in these two registers will be compared. If these two are equal or if this is not equal, then the control will be shifted to this label, this address what is provided by here and all. So here in this case, how this address will be calculated is it's not just this address and all. So whatever the address that is given in the 16 bits, right? So here this is not the byte address and all. This is the word level address here, because to accommodate the more for jumping to a to increase the span of the jump and all. So if it is, suppose for example, if it is directly the byte address, for example, then with that what you can see, that means the shifting will be like the branching will be like up to 2 power 16, up to 2 power 16 locations, byte locations and all. So if you want to increase the span of the branching, then we can in this jump instructions and all. So address whatever is mentioned is nothing but it's a word level address and all. It's a word level address, and then the branching is also done with respect to the current instruction. Right now we are executing some conditional statement, and then with respect to that conditional statement, and if the whatever the condition satisfies or doesn't satisfy, you need to branch, and the branching instruction will be with respect to the current instruction. So the current instruction is at the PC location. That means the PC address specifies the current location. And then immediately, as soon as this instruction is going to execute, at that time the PC will be loaded to the next instruction, PC plus 4. PC plus 4. So therefore, here this the branch address will be computed as whatever the PC plus 4. The recent address is PC plus 4 because the PC is this current execution. And the PC plus 4 is that immediately once the instruction is fetched, then immediately the PC will be loaded by it is incremented, and then it is pointing to the next instruction. So therefore, the target address for a branch is computed with respect to the PC and all PC address. It means the current with respect to the current next the following instruction. So therefore, the PC plus offset into 4. Offset is nothing but this one. This is the 16-bit content. Whatever is there over here is not to be 16-bit offset. And as I mentioned that instead of viewing this as a byte address, here we are viewing this as a word level address. So with respect to that, we will go for actual location by multiplying offset into 4, so that we will get the byte address, and then that byte address will be added to the PC. But the PC will be now it's already incremented. So therefore, the actual address, the branching address will be the PC plus 4 plus offset into 4, where the offset is nothing but this. So it means that with respect to the next instruction, the branch address will be either positive side or a negative side. It's provided by like 2 power whatever the 16 bits are there multiplied by 4. So that much away you can able to branch. That is the maximum branching that can be carried out, that can be possible using the branch conditional operator, branch conditional instruction and all. And usually most of the times that happens, that is sufficient, good enough, because you are doing that means you are performing some conditional operation and all. And mostly these conditional operations and all we do in the loops, or we do in the if then statements and all. So therefore here we need to execute some statements, we have to skip some statements. So for that purpose, whatever this branching will be, it will be mostly it will be very nearby, not and in general, like when you analyze the several codes, you can able to observe that more than 50% of the codes, the branch will be less than 16 bytes. The branch will be less than 16 words or 16 words. So that way, the 16 bits are good enough most of the times. If it is more required, then we'll see the other alternative and all. So that way here in case of branching, we use the PC relative addressing. That means whatever the current PC address is there, for that PC address we'll add this offset multiplied by 4. So that way you can get the desired branch address. Yeah. Then the other addressing is known to be the other kind of a branch is nothing but unconditional branch, or known to be simple jump interest. Jump addressing. That means here there is no condition involved here at all. And so simply the control has to be shifted to some other location. We have seen that in case of when you are executing the loops and all. So we'll follow certain set of instructions and all. Then afterwards, at the last statement of the loop and all, it's simply jump to the original or the beginning of the loop and all. Likewise, the loop will be iterated and all. Loop will be iterated. So for that, if you use the jump instruction. And there is another instruction related to similar to this one, going to be JAL, jump and link. So this instruction is used, jump and link is used in case of calling the procedures or calling the functions and all. At that time, this jump and link will be used, because no, sometimes we are calling the functions where the function may not be in the program, may not be in the same program. That means user may call a function that is available in some library functions, right? So yeah, please mute. I think one of you is unmuted, so please kindly mute. Yeah, okay. So here this jump and the JAL instructions, they are unconditional ones. It means that here JAL, we know that when you are calling a function, we are using this JAL function because this is the jump. That means here the purpose is that we need to jump to the subroutine or a procedure, what you are calling, and afterwards at the end we need to again return back to the calling the caller, right, near to the caller and all. So therefore the jump and link is used in case of procedure calling. This simple jump is nothing but just unconditional jump, where when you are doing the looping and all, at that time the last statement of the loop will be usually kept as a jump, so that you will go to the beginning and all. And here in this case, for both the case, both of them, the addressing format will be this one specific format. This is neither a register R format nor the I format, and this is not to be J format, jump format, where it contains the opcode 6 bits, and the remaining 26 bits are given for address and all. Remaining 26 bits are given for address. So this will give you the much wider or much like longer jumps, whereas earlier one we had given only 16 bits. So with that we can able to jump up to 16 whatever that 16 bits quantity multiplied by 4, that is offset. So with that offset you can jump, right? Whereas here this unconditional jump, where you can provide much wider jumps, or you can jump to much far away, you can able to do that. So that's why here the 26 bits have been given. And again here the way the address calculation will be done here is that whatever the PC is there, whatever the present the PC address is there, and from that PC we'll pick up the most significant 4 bits, because the PC address is like the PC address means the address that is present in a PC or PC plus 4 is a 32 bits. Out of that, the most significant 4 bits will be taken from the PC, and the remaining 28 bits will be filled up with this, because here this is again will be viewed as the word level address, 26 bits, and to get a byte address, again these 26 bits will be converted to 28 bits, because multiplied by 4, that gives you the multiplied by 4 is nothing but shifting 2 bits towards left. That will take care of multiplication of 4. So we will get a byte level address. So we will get total 28 bits you will get here using this 26 bits and all. And the remaining 4 bits you can get from the PC. Like the PC address, whatever is there, the PC or PC plus 4, whatever is there. From that, the most significant 4 bits will be taken and then concatenated with the remaining 28 bits of this. Since it is a 28 bits, we have a scope of much jumping to far locations and all. So that's why this is the way you can able to compute the jump address. And this is just a simple illustration to how these jump and conditional jump instructions will be. This is the actual program what we have already come across in your previous class. It's just a loop statement and all. In the loop statement, you are just incrementing the loop. You are fetching the array elements and all, and you are comparing the array elements with some constant k. And whenever the constant, whenever that condition holds good, at that time we will stop it. Otherwise, the loop will be iterated and all. So these are the set of instructions that are used. Here, if you look at here, so this is the first location corresponds to this one SLL, and this is the 32-bit code, the instruction code corresponds to that, right? Because these are the 2 registers, so these are the 2 registers corresponds to that, right? And then and then this is the shift amount, like 2, because and then yeah, right, and then the next. So likewise, these are the instructions, and here you can see that here there are 2 jumps are there. One is a conditional jump, branch if not equal, and simple unconditional jump is there. And here what happened, this is the loop, this is the end of the loop. So therefore we have to go back to again the loop. We had to again go back to here, and then again the loop has to be carried out. The instructions has to be executed. And this is the conditional one. Suppose this condition met, then what happened? That means here whatever the value, whatever the array element, if it is equals to S5, if it is not equals to S5, then you have to come out. If it is equal, then you have to keep on, something like that. So therefore here branch are not equal. If these two are compared, and if it is not equal happens, then here it has to go to exit. That means you have to come out of the loop. So this loop will be that exit will be there after these 2 statements, after these 2 words and all. So therefore here we have to keep because this is a branch are not equal. So therefore it's the immediate format. So therefore the 16 bits are meant for the offset and all. So here this will be the statement. If it is exits, the control has to be moved on to here, this exit label and all. So this exit label is 2 words away from this. That means after this, the 2 words, the like. So therefore here the offset will be 2 words, and the way it is computed will be like here this 2 times 2 into 4, because this is the word level address. So therefore you have to get a byte address 2 into 4, that is 8 bytes away from the next PC. That is already 8012 is there. So the next PC plus 4 8016. 8016 plus this 8 gives you 8024. So therefore, if this condition satisfies, then the control will move to the exit. So the corresponding that is nothing but the address is this way. So therefore, if this satisfies, then it will go to here 8024. Otherwise, it keep on execute the following instruction, and afterwards, when it comes to here at this last statement J loop, that is nothing but J loop. Here the address of loop is nothing but here again it goes to 8000. So therefore we'll place a 20,000 words, the 20,000 20,000. So therefore what happens is 20,000 will be converted to the byte level. 20,000 into 4 will get 80,000, and then this 80,000 will be appended to the most significant bits of PC, right? So that way you will again get back to this 80,000 and all. Because here you can see from this PC, this is not there will be other elements. The address will be it's much higher and all, but here just for this illustration purpose only, the least significant 5 bits are given here and all. So therefore, if you take a PC, the PC will be something else here, the higher bits, and you will take the 4 higher bits and then append these 80,000. 80,000 because 20,000 into 4 80,000. So therefore it will go back this way. So that way you can able to calculate the addresses in case of branches, whether it's a conditional or unconditional. Like the another one is that suppose as I mentioned that sometimes most of the times in case of conditional branches, you need to move a few instructions away from the control, either forward direction or a backward direction, right? But sometimes but suppose if you want to go for a far jumps, like if you want to make the jumps to very far locations, even in the case of conditional jumps also. So in that case, the assembler will perform this in a different way. Suppose this is the statement BEQ S0 S1 L1. Like but with this, what is the limitation? By using this BUQ, that is conditional jump statement, the label whatever provided will be only 16 bits. That means the address offset whatever is provided is it consists of only 16 bits. So therefore you have a limited jump with respect to the current PC value, right? But actually you want to make the far jumps. So in that case, what you can do is that this statement can be rewritten like this. Like we'll go to the other way, like branch are not equal S0 S1 L2. That means if it is not equal, suppose if it is equal, you have to go to the label. You have to go to the far away jump. If it is not equal, then you have to execute the next instruction itself. So therefore here, instead of writing this way, you can write that branch are not equal. If it is not equal, then you have to go to the far jump. So if it is not equal, then you have to go to then the next statement can be placed as jump L1, where L1 will be very far jump, which is consists of about like more than 16 bits and all. So that way you can go to the far jump if it is equal, right? If it is not equal, then anyway L2, that is L2 is nothing but just one instruction away from this one, like here L2. So that way you can accommodate the far jumps even in the conditional jumps also by rewriting the machine instructions in this way. With this, what happens instead of one instruction, we'll use we need to have the 2 instructions are required. One additional instruction is required and all with the other instruction instead of BEQ, you are using the branch are not equal, and that way you can able to do that, because here if it is equal, we have to go to the far jump. So the same thing we can write in this way. If it is not equal, then go to a jump where it is the jump you have sufficiently large address space is available. You can able to indicate. And if it is not equal, then anyway you have to execute skip this one, and you have to go to the statement that is there at the L2 and all. So that way you can provide the for branches also in the conditional statements. Okay. Then this is just a whole summary of how do we compute the addressing, how do you fetch the operands and all. In case so far we have seen 3 different types of formats: R format, immediate format, and the jump format. Right? We have only 3 formats we have seen. right? In case of R formats, we have the 3 register operands will be there. In case of immediate format, you have the 2 register operands and 1 immediate operand will be there. And in case of jump format, we have only opcode and the rest of the field will be given for meant for the address and all. So in these cases, actually here, based on this here, we can view these address, we can view these instructions with respect to different addressing modes and all. Different addressing modes. One is that known to be immediate addressing. It means that if the operand contains the constant or a value directly, then it's not to be immediate addressing. It means that one of the operand is directly available in the instruction itself. That means there is no need to fetch separately either from register or somewhere else and all. So it's not to be immediate addressing mode. Immediate addressing mode where the constant that is the data value that is present within the instruction itself, it's not to be immediate addressing and all, because then you no need to fetch separately because the data itself is a part of the instruction. And the other one is that R format instruction where the register operand, that means the values are available directly in the register center. That means to get the values or to load the values back, you need to have the register identities or register addresses are required. Register addresses are nothing but their numbers only, because there are 32 registers 1 to 31. And then the addressing the registers are nothing but each register can be addressed using 5 address lines, because there are total 32 0 to 31. So this 0 to 31 can be uniquely represented by using 5 bits. So that way these R format instructions come under the category of like register addressing and all, because the operands are available in the registers and all. So therefore, for fetching that one, you need to have register addresses are required, and based on that you can fetch and you can store the operands also after the operation is over. And load and store instructions, we know that particular for memory accessing and all, the addressing will be based on the base addressing order. That means we will keep the starting address of the array or starting address of the data will be given in some register and all as part of a register. And afterwards, the desired location will be specified as a part of 16 bits offset and all. So that way here, the address will be computed as the whatever the base address that is present in the register plus the offset and all. So that way it's not to be base addressing scheme, right? So that way you can able to fetch whether it's a byte or a half word or a word completely, whatever you can able to fetch by using appropriate instructions and all. And the other one is that just now we have mentioned PC relative addressing. This is used for conditional jumps. For conditional jumps, the address will be mentioned as 16 bits. And since it's a conditional jump, so most probably the desired place to be moved will be like close to the present instruction and all. So therefore, whatever the PC content is there, so PC plus 4 usually, because the PC means it points to the current instruction to be executed. And immediately once the instruction is fetched and it is executing, at that time the PC will be immediately updated. The PC will be pointed to the next location, right? So therefore, here the PC relative address is usually it's a PC plus 4 plus the offset whatever is given. So that way it's not a PC relative addressing. This is nothing but this is usually used in the conditional jumps like branch and equal or branch are not equal and all, where the address will be given in the will be given by the 16-bit label and all, right? And then the other one is the last one is known to be the pseudo addressing, pseudo direct addressing, where here the address will be given in the form of 26 bits. Address will be given in the form of 26 bits. And for this, the address will be generated from by taking the most significant bits of the 4 most significant bits of PC, current PC. And then these 26 bits are converted to 28 bits by converting to byte address and all. Then these 28 bits will be appended to that, so that you will get the branch location or the new address which can be accommodated at far locations and all, because there are 28 bits can be used for moving the branch, moving the control and all. Likewise, there are other addresses. There is one more addressing known to be like you can jump to a register and all. Sometimes no, you can. There is a another instruction to be jump register. It means that actually here where it contains the like the address part, the address value will be placed in the register and all. And by using that instruction, you can directly jump to whatever the register contains. That means the 32 bits and all. To that address, it will directly jumps. Usually, that will be used in the like when you're calling a process procedure, and then when you want to return to that, at that time, we will place the return address in that particular register and all. So that way, even you can use that register addressing for jumps also, unconditional jumps also you can use it. Okay. So this way, these are the various addressing modes that we can come across in the register when you are performing the MIPS instructions and all, like different types. Some may be direct immediate addressing where there is no address is required, register addressing, or the base addressing. With respect to base, we are fetching by using offset, PC relative, then pseudo addressing, or the addressing used in jumps where the content is there in the part of the register. Yeah, this is the last part we are going to discuss in this chapter. So this is right now actually we are discussing about the mission instructions and that are in the symbolic form, right? And here we'll try to discuss about like how this high level language program is is kept ready for running the program by a computer and all, because this is a high level language program where the programmer will write the code in any one of the high level language based on the desired application and all. And as I've already mentioned that these instructions are close to the natural language, so they are not interpreted or they are not directly implemented by the underlying processor and all, because the processor will execute very simple operations like arithmetic, logical, and other operations as we had already discussed and all. And whereas the C code or the high level language program is the instructions which are close to the natural language, and those are not understood, and they are very different from the instructions that are executed by the processor and all. So therefore, there need to be some translation is required from this high level language program to these mission level language instructions and all. And these are the steps that are involved in translating the high level language program to a program that is ready for execution and all, right? So these are the four steps, logical steps. One is known to be compiler, and then assembler. We'll see that each of that, and then linker and a loader and all. So we don't discuss too much of details. At a very broader perspective, we'll try to discuss, and you will can able to understand while when you are going through the operating systems part also. At that time, you will get a much better clarity on this, the overall translation and all. And now here, these are the four steps: compiler, assembler, linker, and loader. And here from the names, the compiler, it will translate the high level language program into a symbolic language. Symbolic language means a symbolic language guided by the mission level instructions and all. Mission level instructions. And the compiler will translate the high level language program into, you can say that, assembly language program. And the assembly language program contains the instructions, whatever we have seen so far, like arithmetic, logical, and so on. Set less than and all of them, right? So the compiler will basically perform the translation of this high level language program to these assembly language instructions and all. So for that, actually here the C program or program in high level language is very compact. That we have seen. Even the single statement of high level language program can be when you're translating, you can see that the multiple lines corresponds to a single line of high level language program and all. So that way the compiler should be efficient enough to translate the high level language program to the assembly language program. And while it translating, it also has to indicate if there are any errors in high level language program, because it should be aware of the syntax and semantics of the high level language, and at the same time the syntax and semantics of this assembly language also. So while doing the translation, it also checks the syntax and other aspects of the high level language. If there are any errors and all, it tries to indicate those errors with the line numbers also. And then it derives the code for the assembly language, and here the compiler have efficient compilers where it tries to optimize the code, assembly language code for the given high level language program and all. And also it should be faster also, because there are huge amount of code, and in that case the compiler should be faster enough so that it can able to compile faster. And then it also involves in the runtime and other, it also involves in the execution also. So therefore there should be compilation should be faster, and the optimal assembly language code has to be derived, right? And if there are any errors and all, those errors should be brought out. And so that way the compiler output will be your symbolic language, assembly language instructions and all. And once we have the assembly language instructions are available, then the assembler will derive the machine language modules or objective, like can say that it's not to be assembly file, and from this assembly language instructions to it will derive into like the machine language codes. The assembler basically like it tries to derive the corresponding machine language code for every instructions one after another and all. So while doing that, the assembler, when you're performing the conversion from assembly language, the symbolic instructions to the machine language instructions and all, so it will do certain part most of the times. If the instructions are straightforward, then you can able to derive the machine language code first for those instructions and all. Suppose if this machine language, if the assembly language instructions points to some procedures or points to some data where the data is not available in the current program or current in the assembly language program, it maybe points to some other files. So at that time, the assembly language program, the assembler will provide, will indicate in the symbol table, where in the symbol table it just mention the symbols and then indicating that their references are not available at that particular point of a time. That assembler is not aware of that, right? So that way the assembler will will basically convert the assembly language instructions to machine language codes. And then if there are some references which are not resolvable, those things will be mentioned in the form of a symbol table. And then so that way this assembler will derive the objective modules from the that those are not to be objective module. We'll see that how the objective module looks like and all. And so that way the assembler will translate the assembly language instructions into machine language, and then with some other information which is used for like running the program later on and all. And likewise here the assembler will derive these object modules, like multiple object modules and all. Like for example, you can see assembler language. So it for the program, sometimes no program itself will be split into the multiple modules for the convenience of, suppose if the modules are independent, they can able to run also independently parallelly. So for that purpose here, the modules will be like whatever the different modules are there. For every module, we'll assemble them, nothing but just converting that into the corresponding machine level codes and the references which are not resolved at that point of a time. Because if the instructions are there, if the instructions all are there in the within the program, within the module, then it can be done. But some instructions, they refer to a data or they refer to a procedures which are in some other modules or some other files. So at that time, the assembler cannot resolve that. So therefore, they will be made in the form of a table known to be symbol table, and where those symbols are indicating that those references are not they are not resolved and all. Like for example, when you are writing a program, you are using some printf statement and all. So printf is a function call, and that function call is not part of the user program and all. That function program actually is available in some library routine like SDDIO or something. So therefore, in that case, actually here the assembler will not resolve the location of the printf and all. So that has to be located, that has to be resolved by the next system program known to be linker and all. So that way the assembler will derive the objective code for each of the modules and all, for each of the modules. Like this is the user program. So likewise other user programs also it will derive. So likewise for all these user object modules, that will be later on, that will be linked by the linker and all. So here the linker job is to, like, it will just link all these object modules like one after another in a sequential way. so that it made it just almost like it's just stitching all these modules together, whatever is required for the given application program and all. Like as I mentioned, one example, application program requires a printf statement, like has to execute a printf statement, and for the printf statement where that is available in the some library thing. So that library routine has to be added by the linker here and all appropriately. Likewise, suppose the data is available in some other file, so that file also has to be added by the linker and all. So that way, the linker will take care of these unresolved references. That means the addresses which are not found by the assembler. So those will be derived by the linker, and they will add all of them put together into a single file known to be executable file and all. Known to be executable file. So this executable file contains almost like all the references are available, all the addresses are available by this point of a time. Then once the executable file is available, then it is placed in the secondary memory, and then afterwards, whenever you want to run this program under, at that time, a loader is known as another system program supported by the operating system and all. This loader will fetch this executable program and put it into a memory, and then start initiating the start execution of the program and all. So that way, this is a high level language program, and this will be want to run this program and all. It has to undergo through these stages and all different stages. And one more thing, when you are when the compiler performing the compilation, it means deriving the assembly language instructions and all. To perform to make it easier, the compiler sometimes it will derive the assembly code instructions which are not actual machine instructions and all. For example, these things, like for example, move contents of one register to other and all. So this is not the actual machine level instruction. So this will be implemented by using some other instruction like add. But for the convenience, actually we'll just use this particular symbolic code, symbolic instruction, assembly instruction, which is not the actual machine instruction, but this is the way the compiler will use some other assembly instructions which are not actually available at a machine level language. It is not a part of the actual instruction set and all. Like for example, BLT, the branch less than, or branch greater than, branch less than or equal, branch greater than or equal. All these instructions, and they are very frequently used to come across in the high level language and all. So, but for them, the equivalent machine level instructions are not available directly. But for the convenience, the compiler will use these particular assembly instructions directly, the BLT or BLE, branch less than or equal, greater than, all of them, even though they are not actually supported by the machine language, but they were used by the compiler and all. So now the assembler job is that actually all these machine instructions, suppose there is straightforward instruction like add, like for example, R1, R2, R3 and all, it's a straightforward instruction where the register numbers are known to the assembler, and then the opcode is known. And so therefore directly that instruction translation to a machine code will be directly carried out by the assembler itself. But for these things and all for move or BLT, there is no opcode is available, right? So it's not the actual machine instruction. So therefore, these instructions will be again translated to the machine instruction, the corresponding machine instructions, like move means this one. And whereas in case of BLT, it is resolved into like two instructions, kind of SLT, then followed by BNE. So likewise, these assembler will derive the actual machine instructions from the assembly language code, where the corresponding machine instructions are not directly available. So these instructions are known to be pseudo instructions. These are known to be pseudo instructions, right? So that they are not actual machine instructions, but they are but they are represented in a symbolical way. But the assembler will take care of that one. So therefore, this is also a part of the job of the assembler and all, where if such instructions are there, because with that actually the compiler, the assembler has a rich set of instructions, so that the compiler will directly convert that into these simple instructions. But later the assembler will figure it out, and it will replace these pseudo instructions with the actual machine instructions and all. So this is one of the job of assembler. And next one is that, as I mentioned, that assembler will derive the assembly language instructions to like the machine instructions. There's known to be object module. It will derive the object module .o files and all. You can see that it translates the program into machine instructions and provide the following information. Like assembler will assemble derive the machine code the module by module. That means it contains the header, the objective file contains the header, which contains the information about the contents in that module under. That means what is the size of the instructions, what is the size of the data. So those information will be given. Like with the text segment means the translated instructions directly. Static data means the data is provided, data is available directly, allocated for the entire life of a program and all. Relocation information means the contents that depending upon the actual locations of the loaded program. And a symbol table is that I already mentioned that these are the global definitions. It means that these references are not available, these addresses are not available to the assembler at that particular point of a time, but later it will be derived. And it also contains some information related to the debugging information, because it contains because the compiler will derive, and that information also will be appended, will also placed as a part of the objective module. Yeah, now if you look at this program, you can see here there are two object modules. You can see here the object header is there, and here this entire part is one object module, and this is another module and all. This is another module. In the object header, first it maintains that the text size data set. Text size means the basic instructions, whatever. So the text size means the instructions will occupy a space of about 100. It's in the hexadecimal thing. It's an hexadecimal notation. And the data is occupying about 20 locations with respect to hexadecimal notation. And now then after giving the header and all, now the text segment will be there. The text segment is nothing but just the instructions. Here these instructions will be like if there is no, if the references are available, then this entire instruction will be translated to machine code. The assembler will place them in the form of machine code and all. But here just for representation purpose, just for interpretation, this is just showing that these are the text segment. That means that corresponds to the assembly language code, it corresponds to the machine codes, corresponds to that. Load word something, and then jump JAL, it means that you are calling a procedure and all. And here you can see the colored ones, whatever is there here. So those are not resolved. Colored ones here you can see here, they're not resolved. So therefore they are mentioned as 0 and all, because that's not known by the compiler at this particular point of a time. Here load word, this is the global pointer, and then the offset should be required. And this offset may be available in some other file. This offset may be available in some other file, which is not known to the assembler. So therefore, this particular value or this particular location is not known. So therefore, it was mentioned as unknown reference and all at the assembler. Likewise, JAL procedure, and here the procedure may not be part of this current object module. So therefore, it's not known where it is available. So therefore, it is mentioned as 0. So likewise, the data segment over here, the data segment means here corresponds to X is your data segment, right? Here this offset and all, but we don't know where that address is there, right? And the relocation information means here, this just provides you that actually here. So for these two statements and all, there are some unknown references are there. And so here this load word for execution of that one, it depends on the value of X. And similarly, this JAL execution that depends on the this value of B. That means whatever the procedure, wherever the procedure address is there. So that address, based on that, it depends this particular instruction and all. So that way, the assembler will provide the information about the machine codes corresponds to the assembly instructions. And as well, if there is no references are there, those two references are mentioned in the form of a table, known to be symbol table. You can see here X and B. That means B is nothing but some procedure. It is calling for some procedure, but that address is not known. Similarly, it want to load something from using this global pointer, but it's the actual address is not known. That is available in some other file, but that address is also not known. So therefore, here it maintains the symbol table, and here these addresses are not resolved over here, right? And then likewise, then the second module, like here the second module contains the procedure B, for example, right? Procedure B, and here this text size equals to 200 and data size equals to 330, something like that. And these are the text segments over here, store word and then calling some procedure. And here also store word, we don't know the word where to store and all. And like jump JL, and here also we don't know the address of the procedure where it is calling. And here, if you look at the symbol table and all, you can come to know that here. So these are the relocation informations, right? The depend because store word depends upon the Y, because you can see that we are assuming that this is the offset is Y, and that we don't know the address of this Y and all. And similarly, JAL here, that means you are calling some procedure, but we don't know where that address is. That's so assuming that procedure it's calling is A, for example, but we don't know the address of A. So likewise, this Y and A happens to be symbol table for the second objective module and all. So likewise, the assembler will try to convert the assembly code into the machine code by leaving these the references which are not resolved, the addresses which are not known at that particular point of a time. It maintains in the form of a symbol table, and then the linker will takes care of this one. The linker by knowing the addresses and all, so it will try to like resolve these references and all. Yeah, this is the linker. Anyway, as I mentioned that the linker used to like the assembler will assemble the module by module in the different modules. And then the linker job is to merge all these segments and derive one single executable file. So while doing that one, whatever the references that are not resolved by the assembler and all, they had to be resolved. They had to be resolved by using the location, by using the references that are available and all. Yeah, you can see the example, then it will be clear to you. For example, the previous one, whatever we had discussed, in case of assembler, we have two modules are available. We have two object modules are there. One object module is a procedure A and the other one is a procedure B and all. Now we are merging these two using a linker and also resolving the references and all. You can see here, this is the executable file, and in this executable file, you can see that since you are merging the modules and all, so the text size equals to 300 hex. So why you got 300 hex? Because we have two object modules, and where one of them contains the text size of 100 hex and the other one is a 200 hex. Then altogether, when you put together, so this executable file requires a size for keeping a text text instructions. It requires the 300x space and all, right? Similarly, for data size also here it's mentioned as 50. This is because in the previous two object modules, if you see, so this is for first one where the procedure A requires the data size of 20 and for procedure B requires the data size of 30. So therefore, when you are combining both of them, here requires a data size of 50 hex, right? And afterwards, you have to place the text document, because you know that here this is the way the memory, the program will be loaded into memory. That means after some reserved space, then after that you have the text segments will be placed, or the text portion or the instructions will be placed, then the static data, then the other information and all. So here the text will be started from something like a 40, then 000 hex kind of a thing. So therefore here also you can place the text segment, like because the total two segments were there. Like the first segment will take the 100 hex and the second segment will take the 200 hex, right? So therefore the first segment related text is placed over here. You can see that is corresponding text, the instruction words and all, like load and jump to other procedure and all. And afterward, this is 100 hex is required because the procedure A, you can see that the text is 100 hex. So therefore now by knowing that, actually here it starts from the address from 4000, because the text starts from here and it gives the first segment will be placed here. And then after the 100 hex, then the second text segment will be patched here, will be placed here. So this is the second text segment. So these are the two text segments corresponds to the two object modules and all. If you look at here, so these are the two text segments. There's a text segment 1 and this is the text segment 2. So they will be placed here in the appropriate locations. Then coming to the instructions here and all, you can see that the earlier these references are not resolved because the data, we don't know where it is, where to be placed and all. So now here, that's the reason that here the 00 will be given unresolved. The symbol table also X and B, these are unresolved and all. And now they are resolved here and all, because we know that the X is available at the the first data item that is placed at the global pointer at the 0 location. The global pointer is there at the middle, like 8000. That is a global pointer. Immediately, the data corresponds to the first segment or the first object module is placed. So therefore, the X is placed at 8000. X is placed at 8000, and the corresponding data corresponds to the first segment, the first module will be placed up to 28, because you know that the data size equals to 20, right? For the first procedure, data size equals to 20. So we started the data from 8000 because we know that here in the static data where the global pointer is at the middle. So therefore, at the beginning, we keep the data that is 8000 to 8020. Data corresponds to the module 1. And then the remaining 8020 to 8050 will keep the data corresponds to the second one. Data corresponds. So that you can able to see in the data segment here, we are keeping the data like starting from here, like where like a 10,000 onwards, we are keeping the data 10,000 onwards. The data is there and all. And in that we are placing the data at appropriate places and all. So this is the starting location of the data for the first segment. This is the starting location of the data for second segment and all, right? And these are the offsets and all where the data is available at 8000 and 8020, the corresponding offsets where the data is available. These are the base pointers. These are the base addresses of the data and all. So that way you can able to resolve. And then coming to the ones here, the JL here, the procedure, because here the procedure A is calling B and the procedure B is calling A and all. And here the procedures are nothing but they are in the text and all. So therefore the procedure A is procedure B is starting from 100 because we know that procedure 100, and the procedure A is starting from 000, that is 4000. So therefore these addresses also will be resolved by the linker and appropriately placed and all. So now all the addresses, everything will be resolved. So now this becomes your executional executive .exe file or executable file, and this will be placed in the memory and all. So that the loader will do that. The loader actually the executable file will be placed in the secondary memory, and then whenever you want to run this program, whenever you just run the program by the mouse click, at that time the loader will place this executable into a main memory, and then it will initialize the instructions and all those things to put it in a like the start running the program under. It will do this one. Read the header and find out the segment sizes and all. By looking at the executable file, you can see that it comes to know that like what is the size of the text, what is the size of the data. It will just find from this header, and that will find the appropriate address space in the main memory, and then it will place the text and the data into that, and also set the arguments also into the stack, because we need to run the program. Is the program has to be run starting from a main program and all. For that main program, whatever the arguments are required, those to be placed in the stack, and all these instructions, all these registers will be initialized, and then jump to the startup routine. That means from wherever that here is nothing but the main program, the main function. It just the PC will be loaded with that main or whatever the address of that, and then arguments, and then call the main function. And whenever the main returns, that means the entire procedure or entire the program is done, completed and all. Then the program will go to complete state. At that time, there is a system call. That means the operating system will take care of that one, because now the user program, whatever, it reaches to the last point, and then the program is end there. So therefore now to pick up the next program and to run that one, then the control will be given to the operating system and all. So that will be carried out by using some exit system call and all. It is nothing but when the program reaches to the last statement of execution, at the end of that, the program, the control will be transferred, because there is no more instructions to execute. It's nothing but the system is the program has been completed. So therefore immediately the control has been given to the operating system call. So that is given by using again calling some system function, which control will be transferred to operating system. Then operating system will load the next program based on on this one, the user input. So this is the way the program from high level language program will be executed by the computer by processing through the various stages: compiler, assembler, linker, loader, and so on. So at this point now we'll stop here. So let's take a break, and after that we'll continue the next topic. Yeah, yeah. Let's take a break now. Yeah, break for 5 minutes, then we'll come back. Okay. Yeah. Okay. Okay, welcome back. Let me see whether. Yeah, right. Okay. So, so yeah, welcome back. So, have any questions so far? Hmm? So that basically the last part, whatever I discussed, the translate, that means yeah, different stages that are involved in high level language program to the execution of the program and all. So those things you need to have some careful reading is required. You have lots of gaps, maybe experience, but when you go through the textbook and also some of them will be get cleared, and some of them will be cleared during our operating system course and all. So, but it is very essential because all of us or all of you have, like, without knowing that you have gone through that, you have already you have written a programs and you are all of them are executed the programs and all. But it's better to know that what is the process that is involved, like the moment when you are writing a program and when you are just simply like double clicking the like when you're doing compiling and afterwards when you're clicking that for running the program. So what is that? What are the different things that were happening and all? So it will be nice to see. So please go through the material that's there in the text, and as well the corresponding for this particular topic, more details were given in the appendix of the textbook. In the appendix again the details were given, very clear details and all. So please go through that there. If you have any doubts also, that will get clarified and all with some good examples or good illustrations it was given there. Yeah. Yeah, the next thing is that actually we are going to discuss here is, so far we discussed about instruction set architecture. It means what are the basic instructions where the machine or the hardware will execute or will implement them, will run, will perform, will basically run, will basically execute them over the using the hardware. You'll implement those instructions and all, right? It means that given the 32-bit code corresponds to instruction, then the job of a hardware will be it will try to decode, it will try to interpret what that instruction is that, and it also fetches the desired operands and performs the operation over the operand, and then it will do the next job, like where to perform the result and also that is the way it used to do. More or less, most of the instructions will go by that instruction. It will try to fetch the instruction, then it has to understand what the operation has to be performed, what the instruction is supposed to do. And for that, wherever the data or whatever, wherever is available, it will come to know based on the instruction format or whatever. Then it fetches, it performs the operation, whether it may be arithmetic operation, or whatever and all. And then the result will be placed in appropriate place, right? So that entire thing will be done by the operating, will be done by the hardware. Yeah, right. So yeah, hello. Yeah, yeah. Please mute. Right. I think one of you has unmuted, so please mute. Yeah, right. Right. So, 'okay. So, so for that, actually, here this regard, we'll 1 minute. Yeah. Sorry. So can you see the slide? Sorry, actually there is some interruption has come in between. Hello? Hello, students?
Yes, sir.
Yeah, can you see this slide? This slide is arithmetic for computers, right? Is the same slide you are seeing?
Yes, sir.
Hello? Okay, good. So yeah, what I'm saying is that so far we discussed about instruction set, and so now we are moving to the next one. Yeah. Hello, please. Yeah, please. One of you. Yeah, please. One of you. One of your mic is on. Please switch off. Is that
Azim, Soget, please switch off your mic.
right? Okay. Thank you. Okay. Yeah. Right. So yeah, here now we are moving on to the basic circuits that are implementing the arithmetic operations. So there are the hardware, the processor contains various components. In that, one of the component is the crucial one, is the arithmetic operations which used to perform, that is addition, subtraction, and along with that the other operations also, like logical operations, comparison operations, and so on. So we'll see that what is the circuit or what is that component that involves, how it performs the varieties of operations by a single unit and all. So those things we'll try to discuss in this particular this one chapter and all. So where we basically focus on the basic arithmetic operations like addition, subtraction, multiplication, division. Again, this multiplication division is again in turn will be performed by using the addition subtractions only, right? And then in the process, we just mentioned about what is meant by overflow and all, right? That is also we discussed. And because of due to lack of time, we are not able to like discuss about these floating point numbers and all, floating point real numbers and all. So mostly because floating point real numbers means the numbers that are with the decimal part, like the fractions where the results into the decimal part. So those things are known to be those numbers, those values are known to be floating point values. And how do you represent that? How do you deal with the arithmetic with the floating point numbers? So that's about the floating point numbers. But due to the limitation of time, we are not dealing with these floating point numbers at this moment. So we just limited to the integer numbers only, like the arithmetic over the integer values, right? So and this is very intuitive, like mostly the way the arithmetic is performed in a normal way, like the way we do in classrooms in a normal in a lower classes, the way we do the same thing analogy will be used over here also. And here you can see this is simple the addition, like here the digits in the black indicating the numbers to be added here and all, the 7 and 6 here. So this is the 7, this is the 6 over here. And if you want to perform addition, then you can perform addition like you know that 1 0, then there is no carry at all. And then again 1 1 results to 0, and there will be carry here, carry will be generated. So likewise, when you look at this addition, like you can see that the addition consists of not only addition of these two bits and all, bits of a number. Along with that, there will be another bit also will be involved. It's known to be carry. It's known to be the carry input that is derived from the previous bit addition, the previous bit addition and all. So that way, when you are performing a 2-bit addition, it involves actually the 3 bits addition and all. And the third bit is coming from the carry and all. Third bit is coming from the carry and all. So that way, the carry also involved also participates in the process of addition and all. Yeah, now before going to this actual addition and subtraction, let us see that when you're performing addition, suppose when you're performing two 8-bit numbers addition, right? And when you perform addition, sometimes when you perform addition, what happens is that actually the value to represent the outcome of that is not sufficient to represent in 8 bits and all, right? That happens. For example, if you have two 8-bit numbers, like two 8-bit numbers, like two positive 8-bit numbers, for example, when you try to add, sometimes, because we know that in the case of 2's complement, for example, 2's complement notation. And suppose if it is 8 bits means the entire range will be, it's not like the entire range is 2 power 8, but in the 2 power 8 you can see half of that will be approximately, half of that will go into the, will be represents the positive part, and half will be represents the negative part, and half will represent the negative part, right? In case of 2's complement, if you look at if it is 8 bits, for example, 2 power 8 possible values will be there. That is 256. Out of 256, 128 values, that means 0 to 127 positive values will be represented, and -1 to -128 will be represented. Total will be like -128 to +127. So that was the total range that will be accommodated by the 8 bits in case of 2's complement notation, and all. That's what we have seen. And here, when you are performing addition in this 2's complement, addition or subtraction, the 2's complement. So when you are adding a positive number with a negative number, we don't have any problem. In the case of 2's complement, when you are adding any positive with any negative number limited to 8 bits, then the result will be accommodated in the properly in 8 bits itself without any error at all, no problem at all. But when you are performing addition of 2 positive operands or 2 negative operands, when you perform addition of 2 positive or 2 negative values, then it may leads to overflow. Because take an example, if just mentioned that 8-bit 2's complement notation, right? You can able to represent the numbers from +127 to -128. So when you try to add, for example, 60 and 80, just 60 and 80, both 60 can be represented in 8 bits 2's complement, and 80 also can be represented in 2's complement notation. When you try to add these two numbers, the result will be 140, right? And that cannot be accommodated in that, and you can able to see that the sign bit will go wrong. You can able to, when you perform addition, you can go that, you can see that 140 means where you will get the 8th bit, the most significant bit will be 1. But in the 2's complement, the most significant bit indicates the sign quantity, sign value. It means that when you're adding two positive numbers, you may get the resultant, the resultant value will be negative, may happen. That is because of overflow, right? The same way when you try to add two negative numbers, when you add two negative numbers, there also you can able to observe that the sign becomes alternate. That because when you're adding two negative numbers, we know that they expected that the value should be negative. But if you get a positive value, it means that that means there is the overflow has been occurred and all. So that way you can able to determine the overflow in case of addition or subtraction with the sign numbers by using the sign bit and all, by using the sign bit. So that way you can see that by adding the two positive numbers, if the result is, if you see the sign bit as 1, it means the negative, the value is negative. So, but that is because of overflow. Likewise, the negative numbers also. The same thing for a subtraction also. In case of subtraction, it is a reverse. It is reverse. It means that when you are performing a subtraction between the positive numbers or between the negative numbers, you don't get a overflow. Because why? When you're performing a subtraction between the two positive numbers, means suppose 7 and 6 are the two numbers, and when you're performing a subtraction, when you want to perform a subtraction, a 6 from 7, for example, then what happens in the case of 2's complement subtraction? What you are doing, like what we do is that, so the number which need to be subtracted, so that has to be negated. It means the 6 has to be negated, and then we have to add to the other number. That means even though the subtraction also can be carried out by using addition, but for that what we do, the sign will be changed. That means we'll negate the other number, and then we'll try to add the negated number to the other number so that the subtraction will be resultant. So when you're doing that, what happens if the numbers are same, and if you want to perform the subtraction between the numbers having the same sign, what it means, it is nothing but addition of positive number and a negative number, or addition of two numbers with different signs, right? So that again results to be like no overflow at all, because as we have seen in the case of addition, we have seen that when you perform the addition between the two same sign numbers, then the overflow will occur. Either you perform the addition of two positive numbers, or when you perform addition of two negative numbers, the chance of overflow may be there, right? So the same thing can be, otherwise the overflow will not occur. The same way here also. The same way here also. When you try to perform the subtraction on the two numbers having the same sign, then the overflow will not occur at all. Because that is nothing but when you view that in the form of addition, it is nothing but when you are performing subtraction on the two same sign numbers, it means that it's nothing but addition of the numbers having different signs, right? So that way you don't get an overflow, but otherwise you'll get an overflow. Otherwise, you will get a overflow. It means that when you try to subtract between the two numbers where the signs are different, that means when you try to subtract a negative number from a positive number or a positive number from a negative number, you may have a chance of overflow and all, right? So therefore, we can, by observing the sign bit after the operation, you can detect or you can say that whether the overflow has been occurred or not in case of signed numbers. In case of signed numbers. But in case of unsigned numbers, in case of unsigned numbers, if a carry results, that means when you perform the addition or subtraction over the unsigned numbers, assuming that there are 8 bits and all, and in that all 8 bits represents the magnitude itself. There is nothing like sign because we know that it's unsigned numbers, right? So in that case, if we want to perform addition or subtraction, so we'll come to know the overflow only because of due to the carry out from the the carry out or a borrow from the most significant bit, the most significant bit. If something results from that, there is no space for to accommodate that. So therefore, you can say that the overflow has been occurred. So that way you can detect the overflow in case of unsigned numbers. And this is the table just now, whatever I had just mentioned and all, in case of addition, subtraction and all. And if in case of addition, if both A and B are positive and if the result is negative, overflow, and A plus B, for example, if both are negative and the result is positive, then there is a chance of overflow. The same thing in the case of subtraction also. And and how to deal with the overflow? Like in case of some high-level languages, for example, C will completely ignore the overflow. It doesn't bother. So therefore, for execution of, in case of if a high-level language is C program, in that case, for performing these instructions and all, addition, subtraction and all, will perform by using these unsigned instructions and all, ADDU, ADDIU and so on. Because these unsigned numbers and all, the overflow will not be detected at all. But whereas some other languages where the overflow detection is required, they consider the overflow and all, like Fortran and other languages and all. So in that case, if overflow occurs, because for these cases and all, these operations will be performed by using the signed instructions like add, subtract and all, because this add, subtract, ADDI, all these things will operate on the signed numbers. Signed numbers mean the two's complement represented numbers and all. So with the two's complement represented numbers, we can come to know when the overflow will occur. By examining the sign bit, we'll come to know whether the overflow has occurred or not. Right? If a overflow occurred, then we need to do there will be some corrective mechanism can be carried out. Right? So for that purpose, whenever the overflow occurred, immediately the program control will go to some procedure, and where that procedure exception, it's not to be exception, means when you perform this addition and all, you got a overflow, with that you will get a wrong result and all. So to taking care of that one, there will be some a system program or some routine need to be executed for correction or whatever, or just like it may throw a message saying that the overflow has occurred, or there is error in the addition or subtraction, something like that. So therefore, for that actually, when a overflow occurred, where in some certain languages and all, so there will be some exception handler will be there. Exception means that whenever you'll get error and all. So exception handler is nothing but there is again a piece of program where whatever the corresponding exception, whatever the corresponding error has occurred, that error can be displayed, or otherwise that error can be taken care if it is possible. So that way there will be exception handler is nothing but it's a piece of program will do the necessary action against to that particular exception, whether to display the message or whether you stop the program, whatever. So that is going to be the exception program handler and all. So that means immediately whenever the exception occurs, whenever the overflow occurs, immediately this exception handler will be called. Exception handler means the starting address of the exception handler will be placed in a program counter. It's not to be EPC. and then the exception handler will be run, and then after that again at the end of the exception handler again come back to the normal program. If it is corrected, then the program will be continued, or otherwise the program will be discontinued, saying that error has been occurred. Yeah, so that way the overflow will be handled. If it is required, you can detect it, otherwise you can ignore it. Yeah. So now we'll come to the different components that are involved for performing arithmetic and logical operations. We have and just I'm not going to the details, but this is very primitive ones. And here for performing the adder, for example, suppose we want to perform addition of two 32-bit numbers, right? So in that case, you need to have adder is required. Just before going to that, first we'll show that how to perform 2 bits addition, just at elementary level, at a very fundamental level, how to perform 2 bits. Like we have seen that here, to perform addition over here, you can, this is the way we will do the addition. This is the bit sequence of one number, and this is a bit sequence of other number, and we'll perform addition and all, like bit by bit we'll do the addition and all. So in while performing addition, in addition to the bits and all, there will be another carry bit also will be there, that also has to be taken care, right? So that way here, when you perform addition here, like just it's a 1-bit adder. That means you are just the data consists of only 1 bit, two 1-bit data items like A and B. And if you want to perform these addition of these 2 bits and all, like you have the output will be sum and carry. You may get sum, you will get sum, and you may get the carry out will be there. Either the carry may be generated, carry may not be generated. That depending upon the inputs A and B. The inputs A and B. Suppose if A and B both are zeros, carry will not be there. If A and B either of them will be 0, then also carry will not be there. If both are 1, then you will get a carry and all. Then you will get the carry out, right? So this is for just a 1-bit representation of addition and all, right? This is for 1-bit representation of addition. And now here, that means here by looking at here, this is and here the carry in will be there. Suppose this is just for like if you take a generic one, and if it is a 1-bit addition, then the carry in need not be bothered if just 1-bit addition. But if there are multiple, if you have a number consists of multiple bits, then the carry in also can be considered as one of the input, because this carry in may not be required for a least significant bit, right? But later on the carry will be generated, because when you add the 2 bits in the 0th position, the carry may be generated. That carry may participate in the will participate in the next bit addition. So likewise the carry will be there from the later bits and all. So therefore in generic, when you see the 1-bit adder, you have the 3 inputs are there, like A, B, they are the actual bits, and the carry bit will be there. So therefore you have the 3 bits will be there, and when you perform addition for these 3 bits, since they are binary, there are 2 power 3 combinations will be there. These are the you can see the table here. The first 3 columns corresponds to the possible inputs for a 1-bit adder and all. The possible inputs for a 1-bit adder, A, B, they are the actual bits, and a carry bit. There are 3 possible bits sequences. There are total 8 sequences possible. For these 8 sequences, if you look at the carry, if you look at the sum and carry, you can see this is the outcome. The sum will be there, and this is the carry out. This is the sum, and this is the carry out. And now you can see that this is known to be a truth table and all. This is a digital circuit where we are giving the inputs as these 3 A, B, and carry in are the inputs and all. And then these are the outputs. Sum is the output and carry out is the output and all. So there are 2 outputs and 3 inputs, right? And here these are the 3 inputs. The first 3 columns are the inputs, and then the 4th and 5th column happens to be your outputs and all. Outputs. And now for realizing this one, because for example, let us take a carry out, for example, and here the carry out output will be 1 at some particular sequences, right? You can see that the B and carry in, and then here, and for these 4 cases, the output will be 1, and then the remaining places output will be 0. So for deriving this one, you can able to derive these, you can able to like implement these output of carry output using this particular circuit and all. Okay, this is the 4 cases where the carry output will be 1. Carry output will be 1, and after simplification, you can get this is the circuit where these are the inputs, A and B are the inputs, and this is the carry in, that is the another input and all. And so these are the 3 inputs, And then for these three inputs, if you give a different combinations, you will get a corresponding carry out and all. And you come to know that from this truth table, at 4 places you will get a carry out will be 1, and the remaining 4 places it will be 0. So whichever the places we will get a 1, so those places need to be considered and see that what is the input for that. And you can simply derive that output as, like, for example, here A equals to 0, B, C equals to 1. And here A equals to 1, and then C equals to 1, B equals to 0. Likewise, different combinations. And you can able to derive the corresponding digital realization as the sum of the products. Sum of the product. While doing that one, here you can do some simplification. And with that, actually, you need not have all the 4 inputs are considered. The last one is a redundant one, so you can consider only the top 3. With that itself, you can able to realize the carry out. So that is nothing but here you can see here like A bar, B, C, and then so this one, so when you simplify this one, this is the corresponding the circuitry for this one, like for a carry out. Similarly for sum also, you can see that. Similarly for sum, you can see the last call, the 5th column under, where again the sum also have at 4 places we have a 1, and then see that what are the inputs for that. So from that you can able to derive the realization. You can say the sum can be computed by using this particular expression and all. So how this expression will be realized? You can see that these 3 can be replaced by using some AND gate. This also by and there are products and sum of the products. You can able to realize by using sum of the products, and you can simplify also, right? So therefore that way you can able to realize the sum and the carry. Because I'm not going to details about this simplification, all these things, because these already you come across in your digital electronics or switching circuits. And if you have not done, so please go to the same textbook. In this textbook, the appendix is given. So in that the details of these things were provided. So please go through that. So that way you can able to compute the sum and carry, right? And now you can see. So this is your block. Yeah, sorry, this is your that way using adder you can able to generate the sum, right? So then you can use the same. This is your adder circuit now here. Like this is represented by square box where plus is mentioned over here, and where A and B are given. This is the output. And then along with this adder, because we want to perform in addition to along with the adder, we want to also perform some logical operations. So for that you can use the simple gates like this is the AND gate, this is your OR gate. Directly whatever the inputs are there, the bit input, they can be given to these AND and OR gates. So now we have the 3 outputs are there. One is the adder output A plus B, and OR gate and AND gate output A or B and A and B. So the total 3 outputs are available now. And all these 3 outputs, from these 3 outputs, based on the operation, you need to select the corresponding output. Like there are 3 outputs are available by giving A and B as inputs. So you have 3 outputs. A plus B is available here, and here A or B is available here, and A and B is available here. So there are 3 outputs are available. So from that, based on the instruction or based on the desired operation, by controlling these, you can select one among these outputs and all. So therefore, this is nothing but a multiplexer here and all. So the multiplexer has a multiple inputs, and based on the control line or based on these controls input, you can able to select one among these. You can select one among these 3. And here in this case, the control lines corresponds to there are 2 control lines are required because there are 3 inputs. So therefore, you require the 2 bits to control that, right? So because 2 bits, you can have the 4 possibilities will be there. Up to 4 outputs you can able to control with the 2 inputs, right? And suppose you have only 2 inputs, you have to select one among these 2. You have 1 bit control line is sufficient. You have 1 control bit is sufficient, or a line, single line with 1 control bit is sufficient to select either 0 or 1. But since there are 3, so therefore you need to have 2 control bits are required. And with that, you can select one among these. So you can see now this particular block will perform 3 operations and add and OR on 1 bit on a single bit data. Now this can be extended to 32 bits. Now the same thing can be extended to 32 bits. You see that this is your 32 bit ALU. You can say that, and where it can perform the 32 bit addition and 32 bit ORing operation and 32 bit AND operation, right? And these are controlled by these control lines and all operation and all. Right? There's a 2-bit line, and where by giving a proper combination, it selects the either AND operation, OR operation, or add operation. Yeah, now the same thing, like now again come back to your 1-bit block. This is that the same block. Each of them is a 1-bit block, and now you are concatenating all of them so that it can be done. It can 32 bits addition or everything can be carried out, right? So now this is again a 1-bit block where here you can see now we want to add another operation of subtraction. So for subtraction, in case of 2's complement, you know that the way the subtraction is performed is nothing but suppose a minus b you have to carry out. So that means whatever the b value is there, so that will be negated first, and afterwards 1 will be added, right? The subtraction will be nothing but in case of 2's complement subtraction where the number need to be subtracted will be first negated. First it will be inverted, then afterwards 1 has to be added. 1 will be added so that then it becomes then the same adder can also perform the subtraction and all, right? The adder will perform addition normally. The same adder, that means in case of 2's complement notation, the subtraction also can be carried out in the form of addition. For that, the input will be the second, whichever need to be subtracted, that has to be inverted and then added. Along with that, the 1 also has to be added, right? So that way, for performing subtraction, you can see that what you are doing here, because when you're performing subtraction, also it also supports the addition also if it requires. So therefore, for addition, we have a and b directly will be given. But for subtraction, what you need to do here, the b, if it is directly given, that becomes your addition, normally a plus b. And instead of b directly giving, so b is inverted, and that will be given, that will be offering as another input. That will be offering as another input. In case of subtraction, we will choose this one, the inverted b will be chosen and all. In case of addition, we will choose the normal b. In case of subtraction, we'll choose the inverted b. So that way here there are two choices of b are there. Like for addition, 0 to be selected, for subtraction, 1 to be selected and all. So therefore, this is a multiplexer where there are two inputs are there, and to have to select appropriately, we have some control line is required and all, right? Control line is required. If you want to select b, then this should be 1, otherwise it will be 0. So therefore, this will be the b will be given using inverter, and then has to be given adder, and then you can and here for performing subtraction here, that means for 1-bit thing here, that means along with this b inversion, you have to add 1 also, right? You need to add 1. So that add 1 can be done here at a carry in. Instead of carry in case of single bit, usually the carry in will be 0 because there is no previous bit. So therefore the carry in will be by default, it will be 0. But in case of subtraction, where the carry in also will be given, will be set. So it will be set nothing but will be 1. So that the b inversion has been done, and then a and the b inversion, then we are adding with the 1 addition. So therefore the subtraction will be resultant as output and all. Subtraction has resulted as output. So now this is again, you can see here. Again here there are only 3 components over here. So there are 3 outputs here: AND output, OR output, and adder subtractor output. And now here to select the subtractor, for example, what you need to do, you have to select 2, but at the same time you have to make the b invert to be 1. So that it just picks up the inverted version. And with that, what happens? This adder will perform the subtraction and all, right? So that way, the same block now it can perform adder, subtractor, and OR, right? So that way, you can see the next one here. So this block, we are just introducing 2 more operations like NOR and SLT, that is set less than and all. So NOR is nothing but here, in case of in the digital logic, we know that NOR, using a De Morgan's law, NOR is nothing but suppose A or B are the inputs, the output will be A plus B whole bar. That is nothing but A bar into B bar, right? So that way, if you want to perform the NOR output, you can select the AND output, and you need to put A invert and B invert to be 1. A invert and B invert to be 1, because you are giving A invert and B invert 1. Then what are the inputs it is selecting? It's selecting A bar, right? A inversion, and B bar you are taking, and these 2 are given to these AND gate, right? Not only AND gate, these are given to all these gates also, like even OR gate. All the outputs are readily available, but we are selecting only the AND gate so that you can get the NOR, A NOR B. You will get A NOR B, A plus B NOR, like NOR gate, right? NOR output you will get. So the same way like SLT, you know that SLT is nothing but for comparison operation, like set less than. Set less than. It means that there are two register contents are there. That means there are two 32-bit quantities, and you need to compare them. If the first one quantity is less than the second one, then you need to set. Then you need to place one in the register. You need to place one in the register. That means you need to place one. Then you have to set the register contents as one. Otherwise, the register contents as 0 and all. Otherwise, the register contains as 0. So for that, there are different ways you can able to compare. And one way to compare here already, because you have subtractor is already there in your circuit and all, then you can use the subtractor for knowing that whether the former argument is less than the other argument or not, right? Suppose A and B, and you want to compare A and B, you want to check whether A is less than B or not. To check whether A is less than B or not. So in that case, actually, when you are checking that one, you perform the subtraction. You perform this adder as a subtractor first, and then afterwards you examine this one. You examine this bit. Examine the most significant bit of the adder, because the adder result is not the one important. The adder sign bit is important and all. The adder sign bit is important. So from the sign bit, that means the most significant bit will be your sign bit, and from that you will come to know that whether the A is less than B or not. Whether A is less than B or not. Because if A is less than B, then what happens? Your sign bit will be 1, because you will get a negative output, right? If A is less than B, then you will get a negative output. When you perform a subtraction, you will get a negative output. It means that the most significant bit of this result will be a 1, because negative means in case of 2's complement, it will be 1. So whenever it is 1, so then you have to set the register contents, the LSB of the register content to be 0. LSB of the register content to be 0. So that way here, that is less, that means here, but here if you look at here, we are using the adder, we are using the subtractor, but the entire subtractor output is not important, right? Only we are monitoring, we are examining the most significant bit, and based on that you have to set the register contents. You have to set the register content. So therefore here, there is another input that need to be picked up. That is, there is another separate output need to be picked up. It's not the subtractor output. You are using subtractor to make a decision or to set or reset the register contents or the value output value, but you are not directly using this one. So you should not pick up the 2. You should take up the separate output, that is 3, which is activated by less the input and all. So here now you have 0, 1, 2, 3. So therefore here to pick up this one, now you have to pick up the 3. It means that suppose it is indicating that as a SLT operation, you have to pick up the output 3. It's not output 2 and all. Output 2 means it again it's like you will get a 32-bit value. You will get a 32-bit value of the subtraction, whatever is there. But here we want to set the register content as either 0 or 1. Either 0 or 1. If it is a negative, then you have to set. Otherwise, it will be like the 0 will be as it is, right? So to do this one, we'll see that how you can do that. And again, one more thing here, the overflow is also added over here, because anyway we are using this most significant bit for this comparing the less than or. So therefore here you can use by using a most significant bit, you can also use for the overflow detection also. We know that, because if both the inputs are positive or whatever, based on that we already come across that you can detect the overflow in case of signed manipulation and all. So that way you can also detect the overflow from this most significant bit, analyzing the most significant bit. Yeah, now you can see here, this is your 32-bit version of this multi-operation unit and all, add, subtract, and SLT and all. You can see here for doing this SLT, what I'm doing here is that there are 32-bit whatever it's adder or ALU, right? And in that, actually for performing SLT, what you need to do, you have to do the B inversion. We need to do the B inversion, and then afterwards this carry in has to be set. So that now what happens is the entire circuitry will perform the subtraction. And then here our interest is only a most significant bit. So if the most significant bit, whatever it comes, it just will take this most significant bit and it will be placed in the least significant position. And the remaining positions simply we have to feed 0. And the remaining positions simply we have to feed 0. That means 0, 0, 0 and all. And now when you are selecting the less when you're selecting the SLT or corresponding ALU output, what happens is that even though it's performing the subtraction, but we are picking the output only at the less inputs, only at the less input. Here you can see all the less inputs are zeros, because what I mentioned is that in case of SLT, our ultimate objective is that you have a register in that the least significant bit has to be set either 1 or 0, either 1 or 0. That has to be set. That is the outcome. That is the ultimate output. That is the ultimate result and all. Because the remaining bits and all anyway they have to be 0. So therefore here for the SLT, all other bits like from first position to the 31st positions, we will just make that all the inputs are given as 0, right? And the same 0 will be picked up as out. And here, but the least significant bit will be determined by this output, the most significant bit of the subtraction and all. If the most significant bit equals to 1, then the 1 will be there as the least significant bit. And if the most significant bit equals to 0, the same thing will be there. That means all zeros. So it's clear. Now we have 32-bit output will be there. So anyway, all the remaining 31 bits will be always 0. But the least significant bit will be 1 and 0. That depends upon the most significant bit of the subtraction. If A is less than B, then you will get a negative output. So therefore, the output will be 1. Therefore, the most significant bit will be 1. So that 1 will be resulted as the here. This is the 0th position. So therefore, the result, the output will be like 0, 0, 0, 0, 1 will be there, right? And suppose whereas the A is greater than B, for example, then in that case, in the result of the subtraction, the most significant bit will be 0. So the same 0 will be placed even in the least significant bit. Then the output will be all zeros. So that way you can use this SLT, you can incorporate SLT in the same ALU also, right? And one more thing we are incorporating over here, the conditional operator, equal or not equal, equal or not equal. So this also can be done the same way, like here for performing, when you want to check the equality of the operands and all, what one way is that actually you can do the subtraction. When you perform the subtraction between the two arguments, if they are equal, identical, then what you will get output will be 0. You will get the output of the subtractor will be 0. Output of the subtractor will be 0. But here this we have to indicate that in the form of like the other thing, where if you'll take the output of all these things, right, and then give it to the OR gate, give it to the NOR gate, because the output will be all zeros. Then when you add all these zeros using OR gate, then again it will be 0. But we have to know that if they are equal, then we should get 1. Then we should get 1. If they are not equal, then the output will be 0. Then we have to get a 0. That means if they are equal, then we have to say that. So that then we'll come to know that then it will be resulted as we have to show it as a 1. If it is not equal, then we have to show it as a 0, right? So for that, if they are equal, when you perform a subtraction, then the output of subtraction will be 0. That all these 32 bits will be 0. Then you add them, then you OR them, all of them, you will get a 0. Then take a NOT inverter. It's nothing but NOR gate. You will get a 0. You will get that means that is the indication of 0, whether the equality is there or not, whether the two operands are equal or not. If it is equal, then the output will be 1. If it is not equal, then the output will be 0. Right? So that way you can also test the equality condition. And for that, these are the control lines you can see here. You can see here, actually here, among these 4 control lines, you can see the bottom, these 2 control lines will basically make use of the operation of the ALU. Like when it's 0, 0, it is AND operation. When it's a 0, 1, it's like OR operation, right? And when it's the add operation, let me, because the circuitry is adder circuitry, we can use it like a subtractor or whatever, but it's adder circuitry is like 1, 0. It's a 1, 0. And again, for subtraction also we are using 1, 0, but the B will be inverted. You can see here these two, the most significant bits, maybe the last one may be A and other one is the B, like, right? And here in case of subtraction, what we are doing, we are using the adder, but the B will be negated. B is inverted. So therefore the B will be inverted here. That is nothing but inversion will be set here. So that is indication of a subtraction code. And then set less than is nothing but you have to use the B inversion. You have to use the B inversion, but we don't take the output of adder and we don't select the output of adder. We'll select some other output, going to be less output. That is not to be that's why we have to separately indicate it by 1, 1. that is separately indicated by 1 1. So therefore 1 followed by 2 ones, it indicates it will pick up the set less than related one. And similarly 1 1 0 0, it's nothing but NOR gate. So it's a NOR gate, but how the NOR is realized? Using AND gate. Using AND gate output by feeding A bar and B bar as the inputs. Okay, NOR is realized as A bar B bar is nothing but A plus B whole bar, right? So therefore the NOR is realized as the AND gate. That's the reason that the least two significant bits are zeros and then these two are inverted. So that way you can do that. And likewise, you can also take care about the zero output also, like the output zero. That will be whenever we want to check the equality, then this zero will be considered. The zero output will be tapped, and then it can be checked for well branching, jumping, whether branch is taken or not taken, required or not taken. So that way you can have the you can use this ALU for multiple purposes and all. And this is a symbol for single bit ALU for multi operation like. And yeah, the next we will yeah, with that actually the ALU design or ALU representation, how the ALU will be implemented for performing the multiple operations and all. This is a simplistic view. And here, if you look at here, when you perform this ALU 32-bit addition, if you suppose when you're performing adder and all, you see that for performing adder, the carry will be flown through all these stages and all. Like carry will be first of all given as input, and then carry may be generated here. That has to be given here. So therefore, here the carry has to be rippled through all the stages and all. So to know the actual output, the carry has to propagate through all these stages. So there will be delays, certain delay that will be involved and all, like because the carry has to propagate through across all the stages and all, from lower bits to the higher bits and all. So to overcome these, there are adders known to be carry look ahead adder, carry look ahead adder. So in that case, carry need not be propagated through all the stages and all. There will be some circuitry will be there, and that circuitry will decide that whether the carry will be there or not at a different stages and all. And based on that, the action can be taken. That is not to be carry look at adder, where the propagation, it need not propagate through all the stages and all. There are different ways where you can detect or you can predict the carry at different stages, and that can be taken care. So that is no, and anyway, we need not bother about it. Just I'm saying that because when you try to implement this 32-bit or 64-bit adder, this is known to be ripple carry adder and all, because the carry will be rippled through all the stages. So therefore, it involves, like suppose if it's 32 bits, 32 gate delays has to be propagated. It has to propagate through 32 adder delays. Each adder, whatever the delay it involves. So all these 32 adder delays will be involved in the output, resultant output. Whereas the carry look at adder will not require all these things. So yeah, anyway, so likewise, you can see the other two things. There are two remaining operations, multiplication and division. But anyway, the multiplication and division and all, we are not actually performing multiplication directly. We will perform the multiplication again by using adder subtractions and all, multiplication or division and all. So this is at a block diagramic level, we'll try to analyze. So we'll discuss these things in the next class. So mostly in the next class, we'll try to cover these multiplier and divider. And the next week we'll move on to the processor and all, which is very important and like yeah, we'll stop here at this point. Okay. Yeah, right. Okay, so any questions? Yeah, these things I'm just going a bit faster, but they are like mostly maybe I don't know, maybe have different backgrounds and all, but these things I'm going faster because all these things are you come across like as per the prerequisites required. So these are there in your already earlier courses you have already done, and much complicated circuits you have done. This is a simpler one. And just here that, but here the thing what we are doing in perspective of ALU, how the ALU will be incrementally. We just started from adder. We just keep on adding operations one over the other and all. That means a single component performs the multiple operations. For that, what are the various the digital circuitry components that are required, like multiplexers and the other simple gates that are required and all, right? Yeah, so we'll stop here. Yeah, any questions? Yeah, and again, the related thing, actually, the whatever the circuits, whatever the like slides I have shown here. So these are, you may not find these things directly in the chapter, but you go to the appendix where the details of these circuits, whatever I have provided. It means ALU with starting with the adder, then afterwards adding subtraction to that, and then UND gates addition, then the set less than. So all these things, the incremental addition and their corresponding explanation. So it's available in the like in the same textbook as part of the appendix. So please go through that, then it will be clear to you mostly. And even if you have some problems with the digital background and all, if at all, so I think even there are lots of books available. On top of that one, even this book itself, at the end in the appendix, the details whatever is required for this following this particular course, they have been given. So please go through that. So that will take care of it. Even if you have a bit of weak in the circuits and the uh, digital components and all. Yeah. Okay. Yeah. So let me stop the recording.